volts of electricity. And we are going to use the sparks from this equipment to take a look at what lightning is, where it comes from, to put lightning safety to the test, and then to end this presentation by making the biggest indoor thunderstorm that happens anywhere on the planet. Sound good? Yeah. I can't turn the show down at all. There's not a volume knob, so I can't make it any more quiet or any louder than it is. If you or anyone you brought with you today doesn't really like bright flashes or loud noises, or perhaps more relevantly than that, happen to have a little one in a stroller, we do not recommend this presentation for children of those ages. You certainly know your kids better than I do, but if your little ones don't like bright flashes and loud noises, you're welcome to try to stay for the show, but if you do need to leave, don't feel bad, it happens all the time. Sound good? Alright, let's get started. The way the Van de Graaff generator works is very, very simple. Remember, the Van de Graaff generator is the big thing here in the center of the theater. It uses 3 conveyor belts to lift the electric charge from the room that I'm standing over up through that wooden column into the red and blue metal domes up top. You can see those conveyor belts on the video to the left and the right. They're yellow, there's 3 of them. And to make this machine work is wicked simple, as they say in Boston. We spin those conveyor belts at 60 miles an hour. When they're spinning, you can hear them. You can also physically see them up there in the video. Once those conveyor belts get up to speed, you put electric charge on them. The charge gets lifted from the basement to the top of the machine. Eventually, so much charge comes up, it goes through the air, and makes a spark. So at this point, I ask everybody sit back, relax, and I'd like to introduce all of you to what this machine does best. What you just saw is a spark, but I'd like to start off our discussion of lightning and electricity with the idea that just because we saw a spark doesn't actually mean that we saw electricity. And to talk about why that is, I want to introduce you to these things. These are smaller, older cousins of the large quills to the left and the right. Now, given the fact that we just saw 8-foot-long lightning bolts, the sparks that these machines make are, quite frankly, not as impressive. So it might surprise you to learn that that spark is being produced by 50,000 volts of electricity. This is the reason why we don't use 50,000 volts to power our houses. If we did, we'd have that coming out of every plug in the wall of our house, and we couldn't have pets. So in our houses, we choose a voltage that may jump into the air and zap our ankles every time we walk by a pond. 110 volts works just fine. Voltage is a measurement of potential energy. The higher the voltage, for our purposes here in the theater, the bigger the spark. 50,000 volts gives us about a 3-inch spark. 500,000 volts gives us about a 5-foot spark. The big Tesla coils will make about 900,000 volts, which is a little bit. At the end of the show, we'll turn the Van de Graaff generator up to about 1 million. So as the voltage goes up, so does the spark size. One of the things you may have noticed about this presentation up until this point is, one, we talked about lightning, we talked about voltage, but I haven't said the magic word yet. And of course, the magic word is electricity. Right? We haven't actually talked about electricity at all during this presentation, and there's a reason for that. Lightning is caused by electricity, but it isn't electricity. You can't see electricity. You probably noticed that these coils get bigger sparks. It shouldn't be entirely surprising. So we talked about, higher voltage, bigger spark, right? 800,000 volts, much, much higher voltage than 60,000 volts. That is the reason why we don't power our houses with 800,000 volts. Now, one of the things you may have noticed is that the coil on your left made two different sounds, and the coils on your right made a single sound. That wasn't your imagination. I want to talk for a second about where exactly that sound comes from. And along those lines, we're going to talk a little bit about thunder. But to do that, I want everybody to find the Tesla coil over on your right. Can you guys find that giant tower over there? In just a second, I'm going to turn that on. And when I do, it's going to produce 750,000 volts of electricity. We're going to see the results of that, this light, heat, sound. The other thing I'm going to do is take a video of that Tesla coil making a spark. And we're then going to play the video back in slow motion. But first, before we do that, I want you all to watch that coil and take a look at what that spark looks like with their naked eyes. You guys ready? 3, 2, 1. Now, let's take a look at what that looks like if we slow it down. So up here in the video, there's the air, essentially as many times per second as I want. I can basically control it. So what I'm going to do right now is turn this coil on. I'm going to make it start wiggling the air at a relatively small number of wiggles per second. And then I'm going to increase the number of wiggles per second. What that means is that coil is going to go from wiggling our eardrums a few times per second to a whole bunch. And I want you all to watch and listen to see if you can physically see the difference and also hear it. You guys ready? Here we go. And it turns out this giant bird cage here behind me is going to be a model of a car. Now, I realize it doesn't look like a car. It doesn't move like a car either. But this bird cage has everything in common with a car that I need to not die during a thunderstorm. Just like a car, this giant bird cage is bigger down. It's got metal on the side, metal on the top, and metal on the bottom. Just like a car, this bird cage is a door that I can get in and out of, but it's still made of metal. And just like a car, this bird cage, lots of metal only stays with metal now. Well, unlike a car, this bird cage is not ever retired. Because the truth is, not every vehicle that you're in has rubber tires. When you think about it, cars have tires. Trucks have tires, buses have tires, trains don't have rubber tires. They're inconvenient during a thunderstorm. Something that takes you during a thunderstorm, believe it or not, in an airplane. Airplanes have rubber tires, but they fly with tires inside the plane. It doesn't have rubber tires, which means that it's tires that keep me safe. Well, this is going to be a pretty quick ending to this presentation. However, I actually don't believe that tires are important. I believe that in most cases you're safer than a car because your car's metal. And I'm going to prove it to you. And here's how I'm going to do that. I'm going to put my bare, wet finger right on this metal point. I'm going to wiggle the bar so that you guys can see that I'm touching it. And I want you all to sit back, relax, if you can, and watch and see what happens to a million volts of electricity when it is escapes. You guys ready? Here we go. Well, we all agree that I am on fire. We all agree that my hair is not standing up. A car is a perfectly safe place to be during a thunderstorm. Couple things. One, you get struck by lightning in a car, you can't get out of the car right away after you're struck by lightning. However, please realize thing two, lightning can strike objects more than once. How much would it stink for you to be in your car, have to get struck by lightning, then to jump out of the car, scream I'm alive, and get struck by lightning standing next to the car? Thing three, we're talking about lightning, we are not talking about power lines. If you ever see a power line down on the ground, never go near it. The electric charges in a lightning bolt stay on the outside surface of the cage. The charges in a power line, we need a much thicker cage to stay on the outside, so don't go near it, because I'm going to be here for about 20 minutes. We started the show at 2 past. So, I suppose it's time for that thunderstorm. I promised you in the beginning. I know a couple people said, what about the rubber tires? So what do you say we end this presentation by doing an experiment with a tire? You'll notice that this tire is up on 4 little white posts. Those posts are insulators. They are going to keep the charge in the air. I want you all to watch not only the top of the tire when it's struck, but also the bottom. Because as we're watching the tire, I think the sort of wacky thing that you guys are going to see is that when lightning hits a tire, it just goes in the top and out the bottom. While it's true that rubber is an insulator, what we have here is a case of too much lightning, not enough tire. Same thing is true for an outdoor lightning storm. But don't believe me, see it for your own eyes. Again, questions, comments, stories, feel free to come chat with me. If not at this point, sit back, relax, take a hand, cover those ears and keep them that way until the lights turn back on at the end. You guys ready? Sure? Okay. Here we go. Folks, thank you all